Hello, welcome to the video. In this presentation, I will be talking about the Albatross UAV flight descriptions based on the simulations conducted in the Unity project. This is the part of the coursework for the final year unit from the flight dynamics. As can be seen in here, the white and black ball represents the center of gravity, and this blue ball represents the mean aerodynamic chord. That point there, the front bit of the mean aerodynamic chord is the coordinate of 0.0. So if we push it forward, then the z-axis location reaches to 0, and if we push it backwards, the magnitude of the z direction increases. As can be seen here, the aircraft is located on the three mass scales, and these red numbers represents the mass reaction that balances the aircraft mass. And by changing the center of gravity, the location of the center of gravity, so if we put the center of gravity backwards, then we should be able to find out the mass change on each scale. And because we know the dimension and the distances between all scales, by taking moments, we should be able to find out the location of the center of mass. As can be seen in here, the mass scale is located at the front of the aircraft, so that when the engine produces the thrust, which rotates the propeller, the mass scale can measure the thrust produced in newtons. So if I increase the RPM, to maximum, which is 100 RPM, and the thrust measured was found to be 29 newtons. So for the static control test, as can be seen here, that's my chaeyoon ID, and for my aircraft, the rudder and the flap should be reversed. So that if you have a look on the aircraft, you can see that that's the flaps down, and roll left, that's roll right, and that's the pitch up, and that's the pitch down, and also that's the yaw right, and that's yaw left. By measuring each thrust at corresponding RPMs, so the RPMs of from 0 to hundreds, so they are measured and imported through the axle, which can be seen on this diagram, and as can be seen, the thrust and RPM show a fairly good linear relationship. For the dynamic response analysis, when the velocity is decreased from max velocity to stalling velocity, the damping and the frequency is reduced. This means that the response was slower as well. When the elevator is activated, the short period of response is also observed. On changing the position of the CG backwards, and this increased the instability of the pitching motion. Therefore, the change in angle of attack uh, was larger as well. Um, when reduced the mean aerodynamic chord, um, the the response at the short period was larger. Um, the most acceptable CG position for this for the pitching control is found to be at 25% Mach. For the lateral dynamic response, the different amount of aileron input varied the rolling. Lower velocity had lower rolling rates. This was due to the less lift generated on the wings. And according to this, the smaller moments on the aircraft were produced. The damping of the yaw response was much lower than the rolling and the pitch response. For the effect of thrust line with respect to CG, when the thrust line is above the CG, the nose down pitching moment was produced. If the CG is located on the thrust line, there was no moment produced for the pitching. Moving the CG upwards produced the pitching moment with a nose up motion. The decoupling CG position was found to be at approximately minus 0.02. For the flight performance, as can be seen in this graph, the CL versus alpha is plotted in here. With the increase in the flap setting, the CL increases. From the data sheet, the CL is expected to occur at approximately 12.4, and as can be seen on here, all CL max occurs when the angle of attack is at 10 degrees approximately. The CL max are expected to be at 1.2 and 1.4 for 0 and full flap conditions. If we look at the CL over CD across the CL4 three flap deflections, these three graphs shown here shows the flaps at 0, 20, and 40 degrees, and the peak of each graph represents the maximum lift over drag, and the lift to drag ratio gets lowered as the flap angle increases, and the lift coefficient also decreases. The calculated lift to drag ratio was relatively lower than the manufacturer's, which was 30 for the references. When looked at the moment coefficient and lift coefficient for three elevator angles, as you can see in this orange graph, the line passes through the 0, 0. This means that the moment is at 0 at this particular lift coefficient. So this one's for the elevated degree at minus 15. Therefore, it is recommended to trim the elevator at minus 15 degrees for its best performances. So if we have a look on the longitudinal stability, the CL versus CM at different CG locations are plotted on this graph. So the locations are varied at 0.1 to minus 0.1. So when the plot is negative, the aircraft is stable, and if the plot is positive, like this blue graph, the aircraft is unstable. Therefore, the aircraft is stable for for the CG at 0 and minus 0.1. However, when the aircraft is at 100% mean aerodynamic chord, it is not stable. When the CG point is located at the neutral point, the margin is 0, so it is expected for the graph to be horizontal. So the straight line should lie between 0.05 and 0.1, so it should fairly lie somewhere around that. During the flight, the excessive steering inputs during high-speed ground taxiing may cause the aircraft drift, then crash. This could be avoided by giving less steering input when the aircraft is taxiing. This part shows the minimum speed to achieve the wheels off the ground. So if I keep increasing the RPM and look at the speed when it takes off. So the speed required was about 30 to 33. So for the cruise speed at 20 meters per second, the RPM was about 22. That was the input, and the elevator input was around 4.6 degrees. According to the flight radar, the minimum RPM required was about 6 RPM, with a speed, the aircraft maneuvering speed was around 15 or 16. So the maximum trim level flight speed can be achieved at the maximum RPM, which is 100. As can be seen in the flight radar, the highest speed achieved was 37. The angle of attack variation with respect to time was plotted on Excel, and for this phugoid, the time period was about 13.5 seconds approximately. The graph did not show relatively fair results, but the time period was approximated. Therefore, the aircraft can be trimmed and operated at a target speed of 20 meters per second at the altitude of 13 meters.